So we're going to be talking about deep dive and particularly Rook, which is currently a project within CNCF, and EdgeFS as an operator. It's a new operator, which is very similar to what Ceph, but designed for a little bit different use cases. So we're going to be talking about that. A little bit about myself. So I'm founder of Nexenta and CTO. Recently, we just sold Nexenta to DDN. And we gonna, before that, you probably Linux iSCSI. I was a Linux hacker for a very long time. I didn't met with Linux, but for instance, if you're using iSCSI within a Linux kernel, this is what I've done back in 2003, 2004. Okay. So what is Rook? Rook is essentially a orchestrator which is used for in cloud native storage, particularly in Kubernetes, and extends Kubernetes with custom types and controllers which are tailored for storage and solve storage issues. It automates deployment. It does the bootstrapping, automates configuration, provisioning, scaling, upgrading, migration, disaster recovery, monitoring, and resource management. These are all very complex tasks, and if you do this by any other means, you will have to think about essentially re-implementing something which they call Kubernetes. So that's why we're kind of leveraging Kubernetes for these purposes. It is also a framework for many storage providers. It used to be just Ceph a few years ago. Now these days it's modern Ceph. It's obviously EdgeFS. I'm presenting EdgeFS. There are other providers, and I'll talk a little bit more about this later. It is hosted by Cloud Native Computing Foundation, and it is totally open source. So, storage on Kubernetes. What is this really? Okay, so this is the example of classic Kubernetes with 3 nodes, 1 master, or maybe more than 1 master for high availability. And then what do we see? We see processor, we see networking, we see disks. We thought, okay, so why don't we just consume those workers in a Kubernetes and build up a storage, because that's all we need. We need just orchestration. And we want to run our software as essentially pods or stateful sets or something like that, and consume the storage devices and provide virtualized software-defined storage on top. So we essentially deploy storage into the cluster itself, so it runs and managed by the Kubernetes. We harness the power of Kubernetes for that. We automated management by smart software. It's a portable abstraction for all our storage needs. Rook is a framework in a sense that Rook by itself is not a storage data plane. It's just really an orchestrator framework for different providers. For instance, it does the storage resource normalization. It discovers the disks and presents those disks to the provider so they can utilize them. Not necessarily can be just disks, it could be the other persistent volumes which operators can consume. The operator pattern plumbing, so we're leveraging this between the different operators and storage operators. Common policies, specs, logic, this is all we leveraging, testing. And these are the current providers which we have, which is EdgeFS, Ceph, CockroachDB, Min.io, NFS, Cassandra, and more to come this year, so watch out. Now, what's in 1.0? And we just recently released 1.0. We announced this at previous KubeCon. 1.0 has 2 new operators, which is Apache Cassandra and Nexenta EdgeFS. And we're going to be talking a little bit more about EdgeFS today. And we'll talk about multi-home network as example of usage and what we've done for EdgeFS. Okay, what is EdgeFS really? First of all, this is Git-like architecture. And I just wanted to give you this snippet from the Git documentation so you can read about this. And you can kind of will better understand how EdgeFS is implementing the storage within itself. Three important points highlighted in red. One is, if two objects are identical, they will have the same SHA. SHA is a fingerprint signature of the data block in Git. How many of you know how Git operates and using Git today? Raise your hands. How many of you knows the Git and using the Git today? Yeah, I'm surprised that there are any people who didn't raise their hands here, because Git is ultimately the widespread source control management system. Why it's so widespread is because it's a fault-tolerant and highly scalable system. And we saw that if we build storage system with the same similar architecture in mind, we can achieve enormous fault tolerance and availability. If two objects different, they have different SHA. That's how we essentially detect all sorts of errors and corruptions. And then we do automatic self-healing by fetching the data from different sites and regions. EdgeFS objects always cryptographically self-validated and therefore globally unique. So what that means is it doesn't matter where your data or metadata is located, it will always have exactly the same signature. Therefore, I can match this signature and I can do global verification of that signature. You can think about benefits of global cache, for instance, right? It's totally immutable storage. You can cache it, you don't need to invalidate the cache. It becomes really scalable at that moment and very fault tolerant. So same as in Git, any modification or strict modification is fully versioned. Essentially, EdgeFS is a system which manages versions. Whatever you do with the system, whether it is block device, object, file, or NoScale, yes, we support NoScale as well. Any modification to that instance essentially will be versioned. And those versions is what we managing, and those versions is what we distributing across different locations. It is scale-out system and protocol unified object storage solution. Ultimately, it is object storage solution. It is protocol unified in the sense that it supports different protocols, such as NFS, iSCSI. It supports S3, variation of S3 particularly for edge IoT use cases. And it's most importantly designed for geo-transparency and edge IoT use cases. And we're going to talk about this more. All right, so Rook EdgeFS essentially deployed as a Kubernetes operator. So when you see your stateful set, you will see, oh, okay, this is your stateful set representing the targets of the storage system. It's a full service lifecycle management. You can install, update, rolling upgrade, uninstall, reinstall. So the whole thing is managed by essentially so-called custom resource definition. If you want to upgrade, you just open your editor, you edit the version, and it goes to the next version. It knows how to upgrade correctly. It will take care of your interdependencies, which are complex within the storage system, and it will do the right thing. It is also tightly integrated with Prometheus and Grafana, so you can monitor the behavior of the particular data segment. It is easy of use, built-in GUI. That's what we have. Sometimes it is kind of tedious job to go ahead and edit the CRD to change something. So we're sort of providing a GUI wizard which allows us to modify CRD so that you don't need the actual editor to do that. But the editor is good because that's your DevOps style, right? So you can edit the CRD, and essentially commit this to the repository, and then have kind of control of what's been changed, the history of the change of your infrastructure. It is runs in embedded environments as well as can be deployed in very large scale environments as well. When it runs in embedded, it can operate within just 1 GB of memory and two CPU cores. What it does is really consumes locally connected raw disks or directories, and we're actually working on adding a mechanism of collecting persistent volumes as well, like in a cloud, and then present virtualized SDS on top of it. It exposes different data protocols, and one of them, most important one for today, is S3, which represents the Object Access Protocol. Additionally, we provide S3X, which is noise scale abstraction and POSIX-like extension on top of S3. You can do very nice things with S3X. For instance, it outperforms S3 for scenarios like time series databases, big table databases by almost 100 to 100 times. Scale out high performance NFS. By scale out and high performance, this is what really it is. It's going into potentially hundreds of thousands IOPS. You can reach a million of IOPS if necessary. Scale out as SCSI block devices. What it means, you can have many block devices in the same segment, scattered across various persistent volumes or just applications. And when you write to one device, it's really going to be leveraging all the disks and servers and zones connected to it. EdgeFS connected data. So the important aspect of EdgeFS that it can connect multiple segments together. And it's not just one. It can be many segments. It can be hundreds, really. And again, if you remember, I talked about Git and how the Git is architected. Very similarly, we do reconciliation of the versions, and eventually we provide fully consistent view of whatever you want to synchronize. Cloud connectivity. What it means is that we can actually transparently present different object formats as internally just metadata within the EdgeFS global namespace. Block level geo deduplication is critically important because it allows us to save quite a bit of the bandwidth when we transferring data between the links. Metadata only transfers. So because we kind of know the fully consistent representation of all the changes we're making, we can make an assumption that you don't need to transfer this or that particular data block, and all we need to do is just transfer metadata only. This is a tremendous savings when you're synchronizing multiple clouds together. Local caching. Obviously, when you're enabling just metadata, there is no data yet, so we basically have local caching mechanism, which allows us to locally cache, then pin, unpin, and clone the data sets. And intelligent prefetching is also part of it. We kind of do not wait for the IO to complete. We just reading ahead, and that is all built in and transparent to the application. With all that, we get into the geo-transparency, and it's real geo-transparency, where you do not need to think about the data management complexities. You do not need to think about snapshot synchronization and stuff like that. It is transparent to the application. And it builds global namespace, really. The protocol transparency is like, for instance, you can see the NFS files in S3, and you can see S3 file objects in NFS transparently. And multi-protocol, that means you can actually, from one segment right here, have different protocols, whatever your application needs. A little bit more about EdgeFS cloud connectors and what we do. So, most importantly, when you're talking about cloud, you're talking about object storage, right? So we're talking about S3 everywhere, transparently syncing regions. Metadata-only synchronization is critically important with local caching because otherwise you're going to be paying doubles and maybe triples, depends on how many connected sites you have. So we currently support AWS Cloud, Google Cloud, Microsoft Azure, and Alibaba is also recently been added. And most importantly to mention is that it operates with unmodified native objects. So what it means, S3 object in AWS can be seen as OSS object in Alibaba and vice versa. And you can set up synchronization with just metadata, so you don't need to move the data actually. Right. So EdgeFS is really a multi-cloud layer with geo-scalability, which spans network of geographically distributed sites connected as one global namespace. It's a Git-like architecture with fault tolerance and immutable version metadata design. It scales equally well for object, file, built-in NoScale, or block devices. It is geo-transparency. It is always on. It is bidirectional access to the same S3 bucket or NFS export in a different regions. It's automatic. Last writer wins update strategy for S3 object. So what it means, if there are two users or applications updating the same S3 object, the last writer will have a preference if versioning is not enabled for that particular bucket. The snap view groups is what we have as a concept for the NFS and iSCSI synchronization. And the geo-consistency is what we have the snap view groups, which are literally floating with connected geo namespace. So what does it mean floating? By floating, I meant to say that when I create a snapshot, let's say in one segment, that snapshot is transparently will be available in the other segment. You don't need to send it. You don't need to kind of transform it manually. It just appears on a different segment. Any granularity protection, so we protect files, directories, buckets, logical units, NoScale databases. It's all sort of built into the paradigm of geo-consistency. Geolocality and active LRU caching. So what it means is that with EdgeFS, you don't need to worry about latency of access to your data. Your latency is always local. If you have local SSD, your local writes are going to be with the latency of what SSD provides. Your local reads will be with the latency your local SSD provides. This is critically important for edge IoT connected devices because the latency is essentially killing the whole idea. An idea is great. Yes, you need to move your computing to the edge, but how would you do that without EdgeFS? So we need EdgeFS. Applications synchronized asynchronously, and that means geographically eventual. Obviously, we cannot break the law of physics. Ultimately, there is a latency between different locations. Yes, there is a 5G on the horizon. That's going to be another 5 years when the 5G is going to be really available for everybody. But even when it's going to be available, you're still going to have problems of sort of like, okay, my link is disconnected. What am I going to do? So how am I going to reconnect? How am I going to resynchronize and so on? So that's why we designed and developed and brought in the EdgeFS to solve that issue. Use cases to mention. So there are different use cases. I think most important ones are here. The multi-cloud CDN workflow. So obviously it's a classic content delivery network. You avoid full replication. You can do pin-on-pin of local cache content. Synchronization of primary source from AWS, Azure, Alibaba, and others. Cloud high availability. So cloud can fail. Your site can fail. So you need automatic failover. You need some failover over the cloud links. So redundancy is critically important. Operate in offline mode. So yes, so link can be disconnected, but locally we can cache the data up to 7 days, and then we eventually will be synchronizing. And after synchronization is complete, your data will be exactly consistent as it used to be before. Edge AT to and from cloud. So capturing of edge data in a local cache and provide clouds for AI ML processing is something which S3X protocol was specifically designed. And most importantly, we also do not need to send the data if it is deduplicated. And if we send, we can essentially guarantee that what we send is necessary to be sent. Now, access global namespace transparently while avoiding the need for full replication is very important for this use case. And because we kind of rooted into the Rook and we started with Kubernetes, we're natively supporting persistent volumes across clouds. And it's actually bidirectional. So what it means, by leveraging snap view groups and snapshots, you can provide geotransparent synchronization. Yes, it can use just metadata only. And yes, it supports CSI for file and block PVs, and obviously consistency groups. Data segmentation and region awareness is also supported. Means that if you have, let's say, a large Kubernetes cluster and you want most efficient access to the data, our logic will select the closest segment and execute your application on the closest segment. All right, so one of the topics which we wanted kind of to talk today about is networking. Within the Rook, we're currently leveraging just the pod network, which, as you know, in Kubernetes is a one big flat network, which is great, right? Very easy. So you have 1G, 10G, 25G, 40G, 100G, whatever. This is great. But it is sharing same pod network with a converged application. And this is a problem. When we running applications on the same Kubernetes clusters alongside with storage, you probably want some sort of isolation. So not anymore. What we kind of come up with is a multi-home network. And this concept is when we essentially create a different network for different user-specific purposes. And the network which essentially are just responsible for Kubernetes servers, API, kubelets, and so on, liveness, readiness, probes, kind of lives here. With that, you can essentially attach your application which needs specific user traffic to certain networking ports. Will be orchestrated within the same pod, right here. If you want to take a look on a definition, an example, how it looks like here you see, okay, this is the Flannel SDS, and you see there is a Rook EdgeFS namespace for which this network was allocated. We selected Malta CNI for very practical reasons, really. And it's just essentially just first CNI orchestration which we selected. We're going to be adding CNI Genie and Neater later. But ultimately, why Malta CNI? Because it's backed by Intel. And we know that as far as networking, Intel is probably leading the space. So it makes sense to kind of select Malta CNI. It's a flexible selection of SDNs. You can do not just Flannel, you can do Calico, you can do others, you can do DPDK, you can do SRIV, DPDK, all sorts of things you can do with Maltas. It enables namespace isolation. This is an important feature because whatever you define in this namespace will be a network just for this namespace, and other pods will never actually be able to get the same IP address from this network. So it's totally isolated to the totally different networking devices. Okay, what does it mean for EdgeFS? For EdgeFS, from the EdgeFS point of view, it means improved performance characteristics. And we actually have done some work on measuring this. It means improved data security. That means if your application and egress and ingress running on a different pod switch network, there is no way they can see what's happening on a backend. And the backend is often shared between various tenants and users. So it's critically important to isolate the application network from the backend network. And this is how it used to be. So you see it's just one pod network. And now we're kind of transitioning in this particular example to this front-end isolation and back-end isolation. You can have more than 2 networks. It's configurable, it's flexible, and so on. The other important mechanism here is what we gain is improved QoS and SLA. When there is no packets kind of floating from application side, we can better guarantee QoS. It's going to be better response time. Therefore, it's better SLA agreement when it's isolated here. OK, so the demo setup. This is a very typical demo setup, though in production we're running larger setups than this. Here you see 4 nodes cluster. So it's 1, 2, 3, 4 hosts. Now, after the deployment, you will see target pod. In my example, it was 4 terabyte each. So it's like we have SSD for sort of metadata offload. We have HDDs, which 1 terabyte each. So we got 1 pod, 4 terabytes, another pod, 4 terabytes, another pod, 4 terabytes. And it's really a stateful set we're talking about. So this is a stateful set. Additionally, we have S3X deployment. It's a Kubernetes deployment style. So we'll get S3X pod, which will be serving this protocol and connected to the backend and front end. We also have cost bench. It's a workload generator which runs on a separate host just to simulate the behavior and kind of highlight the fact that with multi-home network, you'll get significantly better parameters. Now, if you take a look on Rook EdgeFS cluster CRD, typical CRD looks like that. So what do you see here? OK, so you'll see the name of the cluster. You'll see the namespace. And from the previous slide, you remember that for that namespace, we've done different network. You'll see the image version. So we're selecting 1.20. We'll see the service account for RBAC and other primitives. You'll see the local host directory where EdgeFS is going to be storing kind of configuration of files of each target. And then you'll see some parameters which are coming from the Rook framework, like, OK, we want to use all the nodes, all the devices. We dynamically detect all this configuration and building this totally automatically. And some configuration, like we enabled read ahead. We enabled some optimization for performance, metadata offload, and some other stuff, and some resource limitations. So when we execute this CRD, Rook operator will notice, OK, so this is EdgeFS, and therefore it will execute a particular operator implementation which build up all that for you. So you don't have to edit configuration. It will automatically detect SSDs, automatically detect HDDs, and build most optimal pairs for you. This is essentially all you need to write to get the cluster up and running. You can play with this if you want after. So here we go. So we've done some performance analysis. Obviously, as I've been expecting, the results was pretty much, I was expecting actually better numbers than this, but it's still quite significant numbers if you think about this. So what do we see here? So better response time. So response time is, in case of multi-home, is significantly better by almost 30%. And this is when you're just leveraging one pod network. This is with multi-home network. So you may wonder why there's so many milliseconds. Well, because we have 128 write threads and 256 threads. And obviously, we're bound by the I/O. We have only 16 disks in that system. But I've done this on purpose because I actually wanted to highlight how the system is going to be essentially behaving with multi-threaded application. And the example is just 2 megabyte S3 object transfers, these 3 synchronous replicas, and 6 terabyte of random I/O data set. So it's a real test case, real use case of how a system can benefit from multi-homed. On I/O bandwidth, you'll see actually even better numbers. You'll see 40% better bandwidth with multi-home network versus the just pod network. So we can conclude that with multi-home, if we enable multi-home network, we'll get significantly better response time and better bandwidth. In addition to all other benefits which I highlighted, like better isolation, data security, and other benefits. To summarize this brief introduction to Rook EdgeFS. So first of all, Rook community is growing. We adding more providers. So there are a few providers from Red Hat which are coming out. There are a few other independent providers. We're improving existing providers. We're building kind of new practices, how to contribute. And the top contributors I would like to highlight is Upbound.io, Red Hat, Nexenta by DD, and SUSE. These are the companies, Cloudability, who are essentially putting the efforts into making this better. EdgeFS is emerging to address multi-cloud and Edge IT needs. We added EdgeFS for the reason because we believe without EdgeFS or something like that, the edge computing problems, the complex problem for edge computing will not be solved sufficiently and efficiently. So that's why we kind of wanted to, for Kubernetes community, to pay attention for EdgeFS and how this can be used for those sort of use cases. The multi-home network is going to be available in upcoming 1.1 release, but you also learn that multi-home network can be significant in your isolation for the data security purposes, also improving performance, and it's actually possible to do within the Kubernetes itself without introducing any additional layers or custom modifications. So all kind of clean, built into the Rook, and will be soon available not just for EdgeFS, but also for Ceph. And thank you very much. So I can accept a few questions. I have 3 minutes left. If you guys have questions, architecture, go ahead.
Thank you for your presentation. And I have 2 questions. One, basically, EdgeFS provide the S3 and S3X like API, and the data is stored in local disk or blob storage in public cloud. But I think what's the difference between EdgeFS and, can you compare EdgeFS and the MinIO, I think?
So MinIO, yes, so great question, thank you. MinIO is just object. MinIO is simplistic object. It runs on top of kind of directories of and repurposing existing infrastructure. EdgeFS is more kind of enterprise object, so to speak. It runs at a high performance. It can run on top of raw disks, for instance, and it consumes raw disk without file system. EdgeFS also provides good compatibility with S3 and has additional options such as S3X, which is more designed for sort of big table kind of cloud scalability and geotransparency. Additionally, obviously, EdgeFS is a unified protocol, so you have block and NFS, which MinIO doesn't.
Yeah. Another question is about the metadata storage of EdgeFS. I noticed that you have the LMDB configuration in your configuration, but I think LMDB is not scalable. So
we've done a lot of work on LMDB, but as far as metadata is globally scaled out. So essentially, there's no like centralized metadata server. With this architecture, metadata exists on all the pods, so it's gradually distributed. And because we're using the Git architecture, right, so we can address this very easily because it's always immutable. So essentially, it's a sharding across multiple locations, multiple devices.
But I'm not sure if you just mean the metadata is automatically sharded across every node, but how to guarantee for example, one copy of the metadata is destroyed, or how to do the HA? Or
so EdgeFS provides replica counts and erasure encoding, which essentially gives you high availability.
Okay.
So it is in addition to the segmented storage paradigm where you can synchronize between the clouds.
Thank you.
Thank you. Great questions. Any other questions?
I have a question. Is the EdgeFS open sourced?
So
I couldn't find it in the GitHub or anywhere else.
Yeah. So we have great news. We open sourcing EdgeFS within next month or two. So it's coming out. So this is very good news for Linux Foundation and community. We also will be working with LF-Edge community to make it part of LF-Edge at some point. So it's getting to the full open source, essentially.
Okay.
Any other questions, guys? Thank you. So with that, I guess we can conclude this session. Thank you very much for coming.